Hello, and thank you for joining me for our last piece of information for this unit on astronomy. Today we're going to talk about the life cycle of a star and of stars in general. And so there are some things we're going to learn today. It's kind of a little diagram showing you a little bit of what we're going to look at, but we'll talk about each step individually. And so after this lesson, you will be able to walk through the life cycle of a star for both medium-sized, smaller, medium stars, as well as um, large stars or giant stars. Be able to describe differences between small and large stars as far as life cycle goes and what happens. And then you'll be able to look at a Hertzsprung-Russell diagram and be able to kind of explain a little bit about what that tells us about a star, what we can learn from those diagrams. But all right, to start with, stars form from what we call interstellar medium. And so interstellar medium, interstellar being between, stellar referring to stars, medium being space. So this is the total mass of gas and dust between stars. So between our sun and the next closest star, which is I believe Alpha Centauri or Proxima Centauri, everything in between those two is known as interstellar medium. Everything gas and dust wise in between there is interstellar medium. When you have enough of that collect, you have what's called a stellar nebula, which is a dense cloud of gas and dust. So if we get a bunch of gas and dust in one location, that forms what's known as a stellar nebula. So a big cloud of gas and dust is there. That gas and dust will begin to contract, particles will kind of collide, and we'll look at this a little bit in class, but they'll collide and they'll start to come together as more gravity is built upon itself, more mass comes together, more gravity. And then due to the gravity and the pressure, we get what's known as a protostar. So just like a prototype is your first model of something you're creating, a protostar is kind of the beginning stages of a star, where it starts to heat up, it starts to collect, it starts to form what can be or will be a star. After that, your protostar is going to ignite, and fusion is going to begin. Fusion is the combining of two atoms, so in this case we're combining this hydrogen and this hydrogen to form one atom of helium. This is known as the main sequence of a star, the main sequence stage. This is where our sun is at. So this is kind of the big life portion of a star. This is when the star is living. It's doing fusion from hydrogen to helium, and this is where our sun is currently. After that, after all the hydrogen is consumed, your star is going to lose mass because we're releasing some of that as light. So as the mass decreases, gravity also decreases. And so because we're decreasing gravity, the star is going to get bigger. So it's got less mass, but it's going to expand and get bigger. We call these red giants. If it's a really big star, we call it a super red giant. But for our sun is going to become what's known as a red giant. And this is because the outward force of fusion, the amount of energy produced and pushing outward, exceeds that of gravity, which is holding it in. So I have more pulling out than I do pulling in, and so or more pushing out than pulling in, so it's going to expand and get bigger. When fusion slows down, your outward push is going to then become less. So as we get way out here and fusion stops, I no longer have this. I don't have my outward push anymore. So then gravity is going to take over. And your star is going to shrink. So it goes from a red giant and shrinks down to become a white dwarf, which is this little guy here. Okay, so a white dwarf will burn until it doesn't have anything left to burn, and then it becomes a brown and black dwarf, which essentially means it doesn't emit any more light. If this white dwarf rotates, we call it a pulsar. As it emits radio waves, they kind of pulse out, so it's known as a pulsar for a star. We talked that is the life cycle of a medium-sized star, or normal, what our sun is going to do. If we have a very massive star, which we're going to look at some of those in the future here coming up, but very massive stars, they go from main sequence, and so they run out of fuel, and then they become a massive red giant or a super red giant. And then when fusion stops and that push out, so we have a super red giant, this push out goes away, gravity's going to pull it, oops, drew that one the wrong way. Fusion's pushing out this way, When this stops and is no more, gravity is going to condense this thing, and it's going to collapse. And it's going to collapse really fast. In the center of all this, the reason fusion stops is because eventually they fuse into what's known as iron. So at the center of the star is going to be a ball of iron. You have all these particles on the outside that are still there. There's just not enough energy to fuse them. They're going to come rushing to the center. And when they do this, they're going to collide, and this is going to create all of your heavy elements. Everything bigger than iron on the periodic table is believed to have been created by this process. And so everything's going to come down, it's going to hit this ball of iron, and then it's going to ping out, and this is where we get our pretty, our very, very pretty, very bright supernova star here. This can outshine an entire galaxy. There's so much energy. So this is the explosion that marks the end of a massive star's life. So this one star will outshine all the other stars in the galaxy for a couple days. And so it's going to ping, and then you get this very bright star for a couple days, and then it fades out. Depending on how big it was and how much material collided, you could potentially form a black hole after a supernova. So it's going to ping out, and then there's going to be some that gets stuck because they all collided and they all created so much gravity in here that the mass came together, created so much gravity, it forms a black hole. The black holes have essentially an infinite amount of mass inside an infinitely small space, point in space. So this is all that mass collapsing down to a singularity or a single point. And the reason we know these are here is because light bends, and we'll talk more about that in class. So this is going to be your life cycle of a star. You have your interstellar medium here, which then you get your stellar nebula, which goes to a main sequence star up here. That will become a red giant or a red supergiant. Afterwards, when you get this to collapse, it goes supernova. Smaller stars don't have quite as big of a supernova as others do. Or I guess this is all massive stars. So we had a red supergiant, and then we get supernova at the end. It will either lead to a black hole, a neutron star, or a pulsar, or the material will just hang out here and will eventually form a new star when this all comes together again. Those are your possible outcomes for a massive star. This is the Hertzsprung-Russell diagram. So we have all sorts of different stars and all kinds of different stages. Your main sequence stars, or the main sequence stars we know and can observe, all fit on this little band. And the reason there's a band and they're not a single point is because stars have different temperatures. And so down here, this is all concerned about temperature. So this is the temperature of the star here, with the hottest being blue, your coolest being red. Stars found above that are known as supergiants or giants, and then below that we have our white dwarfs. So this compares your temperature of the star with the luminosity or the light emitted by the star, and that's how we place them on this diagram. But if it is a main sequence star, it will fall somewhere in this band, or very close to. Again, supergiants go up above, and giants as well, red giants as well, and then your dwarfs go down below. But that's a Hertzsprung-Russell diagram. We're going to construct one of these in class together and kind of see how it works. Here's just another look at it, that again, you have your main sequence band, you have red giants, red supergiants. These are blue giants. These are really hot stars that are gone to become blue giants. And then these are your white dwarfs down here. All right, last little bit. Larger and hotter stars live shorter lives than our sun will, and then smaller stars. And the reason for this is the more massive the star is, the more mass it has, which means the more gravity it has. Because of gravity and the pressure created by it, this causes fusion to happen really fast. And so fusion's happening really quick. Your hydrogen is being consumed faster, which means your sun is going to run out of fuel, kind of like a car. Think of it as a big truck versus a small little, I want to say a Prius, but Priuses are, I think, partially electric. But think of a semi-truck versus a car. Which one gets better gas mileage? Which one can run longer? And it's the car because it doesn't burn fuel as fast. Your larger stars burn that fuel much more quickly. So they, in turn, have shorter lives. They burn brighter in the sky, but don't burn for near as long because they burn their fuel so fast. All right, here are your review questions. Make sure you can answer these. If you have questions, please come see me. I look forward to having you back in class in the near future, and we will continue our discussion and finish up our discussion on astronomy and continue on with the semester. Thank you for your time and enjoy the rest of your day.